Welcome back to the AI Research Roundup. I am your host, Alex. Today, we're looking at a cool paper called SAMWISE. That's SAMWISE, which stands for Infusing Wisdom in SAM2 for text-driven video segmentation. The main goal here is to improve what's called referring video object segmentation. This is essentially telling an AI to find and outline a specific object in a video based on a text prompt like the cyclist in red. The researchers built their model, SAMWISE, to do this effectively in a live stream by making the underlying segment Anything To model smarter about understanding language and time, all without expensive retraining. And for those of you who want to dive deeper into the code, the authors released a really well-documented GitHub repository for this work. It has everything you'd need to get started, like the pre-trained model weights and guides to prepare the data. It also includes scripts to reproduce their results on important benchmarks like me-vis and ref-davis. Benchmarks are just standardized datasets that let researchers fairly compare different models on the exact same task, which in this case is referring video object segmentation. Alright, so to really see what this looks like in practice, let's look at Figure 1. This figure shows a great example with a video of cyclists, and the instruction is to find the cyclist in red that overtakes others on the left. At the start of the video, the base segment Anything To model gets it wrong. It just latches onto a different cyclist. This is what the researchers call tracking bias, where a model gets stuck on an incorrect object. But then, as the correct cyclist appears, SAMWISE uses its learnable correction and motion reasoning to switch its focus to the right person. So how does SAMWISE actually pull off that correction we saw with the cyclist? This diagram here gives us the blueprint. On the left, you see the video frames and the text prompt, like cat climbing on cat tree. Enter the system. The key innovation is a new module called the Cross-Modal Temporal Adapter, or CMT. This adapter acts as a bridge, connecting the frozen or unchanged image and text processing parts of the model. This cross-modal temporal adapter lets them share information about both what's happening and what the text is asking for, creating a much richer understanding. Okay, so let's zoom in on that cross-modal temporal adapter I just mentioned. This figure shows its inner workings. First, the video features go through a module called Hierarchical Selective Attention, or HSA. This hierarchical selective attention component is what helps the model understand motion by focusing on how small patches of the video change over time. Then, the real magic happens with two other parts: visual to text attention and text to visual attention. These allow the motion-aware visuals and the text prompt to directly influence each other, creating a unified understanding of both what's happening and what's being asked for. And this figure really shows the practical result of that cross-modal temporal adapter. At the top, you can see the original visual features from SAM2. For this video of a cow, those features are always the same. The model's understanding is static. But now, look at the bottom row, which shows the text-aware features from SAMWISE. With the prompt "the cow walking towards us," the model focuses on the whole animal. But if you change that prompt to "cow swinging its head but not moving," the features adapt, focusing much more on the head. This proves the adapter is working. So, how does that hierarchical selective attention component actually understand motion? This diagram breaks it down. The system doesn't just look at one frame at a time. Instead, it groups several frames together and divides them into these 3D spatiotemporal patches. You can think of them as little cubes of video. Then, it uses a process called self-attention, where each pixel compares itself to its immediate neighbors in both space and time to spot movement. And the hierarchical part, shown at the bottom right, is key. The model does this with different patch sizes, starting small for fine details and getting bigger for broader actions. Alright, so even with that sophisticated motion understanding, there's still the issue of tracking bias, where the model locks onto the wrong object and just won't let go. This figure shows the final piece of the puzzle for solving that, a component called the Conditional Memory Encoder, or CME. In the top example, with the query cat climbing on cat tree, the model without this encoder gets stuck on the wrong cat. But with the Conditional Memory Encoder, shown on the bottom, it correctly switches to the cat that actually starts climbing, fixing the error. So, we've seen how all these components, the cross-modal temporal adapter and the conditional memory encoder, work in theory, But how does it all stack up in practice? Well, this table shows the results. It compares SAMWISE against other top methods on several video benchmarks. The scores are J, F, and J and F, where J measures the accuracy of the segmented shape, and F measures the accuracy of its boundary. And as you can see, SAMWISE in the bottom rows consistently outperforms the competition across all datasets, including MEVIS, Ref YouTube VOS, and Ref Davis 17, with the highest scores. So, with those impressive results, it's clear that SAMWISE is a significant step forward. By cleverly combining a cross-modal temporal adapter to understand text prompts over time and a conditional memory encoder to fix those stubborn tracking mistakes, the model becomes much more robust. This work really pushes us closer to AI that can accurately follow complex natural language instructions in video. That's all for this episode of the AI Research Roundup. Thanks for tuning in. I'm Alex.